All right, guys, we're going to spend 3 days on this because it's huge. All right, this is an upper level mathematical proof. Section 12.4 is proof by mathematical induction. We're going to use patterns to prove that something is true for an infinite amount of terms. And every time you start talking about an infinite amount of terms, things get weird. Okay, so there is a logical principle here that we got to get across, and then we got to get with the technical way of actually getting from step to step. Once you get it, it's not so bad, but I'm telling you at first, this isn't a one look and just understand it kind of thing. So focus up here, okay, guys? Find each partial sum. A partial sum means I'm not going to get the infinite amount of terms. I'm just going to cut it off at a certain amount. That's what a partial sum means. So I hope you trust me that I know how to add. This first one is 1. The second one is 4. The third one is 9. This one is 10/16. This one is 10/25. And this one goes 10, 28, 29, 30, 36. Okay, so we should see two patterns going on here. All right? Pattern number 1, the nth term, that's 1, 3, 5, 7, 9, is the term number times 2 minus 1. So I have a sub n equals 2n minus 1 for any of these terms right here. Okay, think this is the fourth term. 4 times 2 is 8, and 8 minus 1 is 7. This is 1, 2, 3. This is the sixth term. 6 times 2 is 12, minus 1 is 11. Now also, the actual sums. Now that's for the nth term. That just that formula 2n minus 1 generates the last term. But this one would generate the sum, isn't it, n squared? So look, when I have a 6, I'm going to put a 6 in here, I get 12 minus 1 is 11, I get the last term. But also, if I put a 6 in here and square it, I get the sum. So there are two terms, two expressions going on here. It looks to be the case that no matter what term number you pick, the first term will be 1, duh. The last term will be 2n minus 1. You can find this using the a sub n equals a sub 1 plus n minus 1 times d formula, by the way. We had just already seen that one before for an arithmetic sequence. And most importantly, the partial sum at the end, it'll end up being an n squared. Now here's the issue mathematically, and when you get into upper level mathematics, this becomes very important. It looks like, as a quote, because I started this with it looks like, isn't mathematically sound. We need to be able to prove that something like this is true for upper level mathematics. Not because we're snobby, but because we actually want to take big, complicated ideas and put them in the middle of bigger problems later on. You're going to see a monster problem at the end of the semester. It's coming up, guys. Okay, there are examples of formulas that are true for the first several integers, but then don't end up being true for larger integers. So we could think we see a pattern here with the sum formula, but maybe it doesn't pan out. So we need to be able to prove that it's true for all integers. Here is the structure behind proving that a formula is true for an infinite amount of integers. All right, here's the structure. It's a simple idea, but it's going to be weird for you when you first see it, okay? Prove that the formula is true when n equals 1. Okay, and then if you assume that the formula is true when n equals k, which will be a weird thing for you to want to do, prove that it's true when n equals k plus 1. Okay, so look, this is what I'm showing. I'm proving that I can start what I think is true, like this n squared. I think that's true with number 1. So if I put in a 1, 1 squared is 1. Yep, I got it. The pattern works at the start. And then I'm showing that I can move from term to term and have that be true. Now I know that's weird for you. So if I find out or assume the formula is true for like the 15th term, I want to be able to prove that it's true when I get to the 16th term. So here's the theory and the logic. Ready? My professors in college, when they taught me this is how they put it. It's like climbing a ladder. If you can prove that you can get on the ladder on the first step, and you can prove that if you're on a step, you can move to the next step, well, then you just proved you can climb the whole ladder as long as it goes. if you can prove you can get on the first step and you can prove that you can move from step to step, you have proven that you can go as far up a ladder as you want. All right, that's the logic. Now let's get into how some of this stuff actually plays out. Okay, so this is something that's in the middle of this proof. Okay, we haven't got to it yet. For each formula, for a k term, I want you to simplify for a k plus 1 term. Now I know that sounds weird, but just watch what happens. Okay, so I've got k squared times k plus 1 squared over 4. Okay, that's my k term. Now here's what I want to do. I'm going to make a k plus 1 term, and I'm going to simplify it. Okay, so I just substitute k plus 1 where I see a k. There's a k plus 1 squared where there was a k. I replaced it with k plus 1. And I'm going to replace this with a k plus 1. And look what happens. I get a k plus 1 there, and then there's another plus 1. Now I'm going to simplify that whole thing. Okay, so let me go back over here. And so I have k plus 1 squared, so k plus 1 times k plus 1. And then I also have k plus 2 squared. So I have k plus 2 times k plus 2. And that's all over 4. I got a lot of work to do here. I'm sorry, I'm looking at my notes, and my notes look kind of funny here. I think there's supposed to be a plus. I don't think I'm supposed to multiply all of this stuff together. That looks like it's going to be forever. So sneak a little plus sign in here and put a plus sign here, and that's going to make our lives a lot easier. Okay, we'll put a little plus. Sorry about that. So this will be k plus 1 times k plus 1. We know that one. K squared plus 2k plus 1. That's that. And then I'm going to put a plus. And then I'm going to go k squared plus 4k plus 4. And this is all over 4. Okay? If that was a times right there, we would be multiplying for a while. So sorry about that. That should be a plus. Maybe I should type these up before I start them. You know what I mean? Okay, so I'm going to just combine this stuff over here, and I have 2k squareds. K squared and k squared. I have a 2k and plus a 4k, so it's going to be plus 6k. And then it'll be plus 1 plus 4 is 5, and it's all over 4. Okay, now, you got to be feeling a little bewildered, and I'm sure me adding a plus in the middle of the problem didn't help. Sorry about that. But you got to be thinking, what are we in the middle of doing? This is a skill that you got to be able to do in the middle of this big proof that I'm about to show you. Okay, so we're practicing a skill that's going to happen in the middle of this big proof, just somewhere in the middle. So I want to be able to take a term that should have been a plus, my bad. I'm going to put k plus 1 wherever there's a k, and then I'm going to multiply out and simplify it. All right, I'm going to do it again. Ready? Here we go. So I'm going to go 1 plus 5 plus 9 plus, sorry, I got to kind of cut that off right there. I have plus. Ready for this? It goes 4 times k minus 1 minus 3. But I'm not done. It also goes plus 4k minus 3. Okay? That's the entire, this thing here is the entire k term. Okay, so I want a k plus 1 term. I'm going to go to this thing, and I'm going to put a k plus 1 everywhere I see a k. Now, I don't have to square things, so this is actually going to be a little easier. So look, it goes 4 times, instead of k, I'm going to put k plus 1, and then there's a minus 1, and then there's a minus 3. Okay, that's in brackets. And then I'm going to go plus 4, and it'll be times k plus 1, and then it's minus 3. So I took this expression, and I wrote a k plus 1 in here, and I put a k plus 1 in there, and now my job is just to simplify it. So k plus 1 minus 1 is just k, right? So in the brackets I have 4k minus 3, and then after that I have 4k plus 4 minus 3. If I distribute this, I get 4k plus 4 and then minus 3. Okay, so putting all this together, I end up with 8k minus 3 plus 4 and minus 3 is minus 2. That's a simplified version of a k plus 1 term, if that's the k term. Now I'm going to get a little weird, and I'm going to go with a inequality. All right. All I want you to do for now is just work on the idea of substituting a k plus 1 and then simplifying. So this is k plus 1 plus 3 is less than 5 times k plus 1 squared. When k turns into k plus 1, multiplying it, squaring it becomes more difficult, right? So this would be k plus 4. It'd be less than 5 times, well, that's going to be k plus 1 times itself, isn't it? And we're pretty good at that one, so I'm going to write it as 5 times k squared plus 2k plus 1. That's a k squared and plus k, and then plus another k and plus 1, right? I'm doing that a little faster, but you guys are pretty good at that at this point. So it's k plus 4 is less than 5k squared plus 10k plus 5. Okay? And then I really do want to do this one too, even though it's a weird exponent thing. I want you to see it because we're going to use this exponent thing in the middle of this section somewhere. Okay, so I want to, that's my kth term. So I want to go with, here, I'll do it up here just so you guys see what I'm doing. The k plus 1 term, I started it here, and then I kept going until it was simplified, right? This really isn't a term, it's an expression, but it's the skill that I'm after here. Okay, so this goes, to get the k plus 1 term, or expression I should say, it's going to be 3 to the k plus 1. It'll be greater than or equal to 2 times k plus 1 plus 1. Turn that k into a k plus 1, and then don't forget there was a plus 1 after that, so I've got to put that in there. That tends to get a little confusing. Okay. What do you know about exponents when they're being added? What do you know about exponents when they're being added? Let me go over the side, and let me do this. Isn't that, don't you add those exponents, isn't it 2 plus 5? Right? It's 2 plus 5. Okay, so I could write this as 3 to the k times 3 to the 1 is greater than or equal to 2k plus 2 plus 1, right? I could write it either that way or this way. And so I'm going to write this as 3 times 3 to the k is greater than or equal to 2k plus 3. Now, I don't blame you if you're like, I don't know, Larson, that I would actually do this. When we get into this proof, if you run into exponents, you'll see a direction you're supposed to go, okay? Again, this whole page was just trying to get a skill in your head of substituting with a k plus 1 and simplifying. All right, so don't overthink this. Here we go, the next page. Use mathematical induction to prove that the following is true. Well, look what I got to do. I got to show that the formula is true when n equals 1. And I got to assume it's true for n equals k. I got to prove it's equal to k plus 1. All right, guys, this is weird. This is weird. And I'm going to write it out in sentences, too, which also bothers you. You ready? Here we go. I must show that s sub n equals n squared, because that's what we're really saying. The sum is equal to n squared, is true for n equals 1. That's what I got to show. So I'm actually going to say, I'm calling my shot here. Okay, well, a sub 1 is equal to 1, and s sub 1 would equal 1 squared, which is equal to 1. Check. The first term is 1, and the sum of the first terms using the formula is 1. So I'm done with part 1. Part 2, I'm going to call out my shot. I'm going to say what I got to do, and this is going to be so weird for you, but we got to do it. Assuming s sub n is equal to n squared is true, oops, misspelled that, is true for n equals k, I must show that s sub n equals n squared would be true for n equals k plus 1. Okay, so how do we do that? All right, ready for this? Here we go. Assume the following to be true. Assume the following to be true. I'm going to show what it would be like for this to be true for n equals k. Okay, so I'm going to write this sentence out. Then s sub n would equal to 1 plus 3 plus 5 plus 7 plus 9 plus, if I'm looking for n to equal k, wouldn't this turn into 2k minus 1, and wouldn't this be equal to k squared? Okay, Now, on the assumption that this is true, that's my assumption. I'm assuming that's true, and I'm going to use that. I must show that s sub k plus 1 is actually equal to k plus 1 squared. That's what I got to show. Okay? So, I lost my place in my notes. I mean, I'm pretty sure I know how to do this, but anyway, so s sub k plus 1 would equal 1 plus 3. So I'm gonna show k plus 1 terms. Ready for this? So I would have the 2k minus 1. That's the kth term, and I got to show one more. I got to show the k plus 1th term. Okay, so I got to put in a k plus 1 where I see a k to get the k plus 1th term. All right, let that sink in for a second. I assumed that this is true for k terms. Well, there they are again, because I'm trying to show it's true for one more term. So I'm going to add a term by taking the formula and putting a k plus 1 in there. So this had k terms, this now has k plus 1 terms. And I got to show that this is equal to k plus 1 squared. Okay? Now I'm going to use a substitution here from my assumption. Ready? This is really the hinge of this whole thing. I'm going to substitute the part that I assumed to be true, the first k terms. I'm going to leave off the k plus 1th term because I assumed that they're all equal to k squared, that's actually true. So I'm going to say k squared for the first k terms, and then I'm going to have this 2 times k plus 1 and then minus 1 as my k plus 1th term, and I got to show that that's equal to k plus 1 squared. Once I show that those two are equal, this proof is done. I have shown it's true when n equals 1. I have assumed it's true when n equals k, so I'm showing that I'm at a spot on the ladder. And I'm using my assumption to show that it's also got to be true for the next step, so I can show I can move on the ladder. So I'm just going to simply say this is k squared plus 2k plus 2 minus 1, and this over here is k plus 1 times k plus 1. When I put this together, I get k squared plus 2k plus 1, and over here I get k squared plus 2k plus 1. At that point, I put a check, and I write end of proof. You guys, this is an upper level math proof. Other ways people do that is they write like a square and they shade it in. Another way to write it is QED, which I believe is Latin for the end of the proof. You got to show it's true when n equals 1. You have to assume it's true when n equals k and write out what that would look like. Then you have to show what you have to show. You have to show that if there are k terms and then you add one more, it's no longer k terms. It's k plus 1 terms, so it better be equal to k plus 1 squared. Then take what you assumed and replace the first k terms and leave that last term. So you have your sum formula, k squared, that you assumed is true, plus the one more term, and that better be equal to k plus 1 squared. And then you do, this part is easy for you guys. Do the math and you show that it's true. Okay, so I've got one more here to do. I'm going to start out a couple of these, and I want you to try it and see where it goes. Okay, part 1, I must show that s sub n equals n times n plus 1 times 2n plus 1. This is one of the ones we used yesterday, isn't it? Is true when n equals 1. I got to show that's true. Okay, so I'm going to go like this. S sub 1 is equal to 1 squared. That's equal to 1. Or I should say a sub 1, I guess, because it's the first term, right? The first term is 1 squared is equal to 1. And then s sub 1, we'll put a 1 there, would be 1 times 1 plus 1 times 2 times 1 plus 1 over 6. I need that to be equal to 1, or I got to shut this whole proof down, because I can't even show it's true for the first one. So that's going to be 1 times 2 times 3 over 6. That is equal to 6. We're done with part 1. We showed that we can get on the first step of the ladder. Part 2. Assuming, which is a weird thing to do, guys, but stick to the logic of this. if I can say that I'm on any rung of the ladder and I can show that I can move to the next step, I can show that I can climb the entire ladder. Assuming S sub n equals n times n plus 1 times 2n plus 1 over 6 is true for n equals k, I must show, and we do talk like this, like upper level math, we actually talk like this, which is, a little weird. But people have been studying math for a long time, right? Traditions are hard to let go. I must show that S sub n, I'm not going to write the whole thing again, I'll just write S sub n, right? Is also true when n equals k plus 1. Okay? Call out my shot, do it. Call out my shot, I gotta make my assumption first, and then I'll show what I gotta prove, and then I'll prove it. Okay? Assume the following to be true. Okay, I'm just going to say this is true when n equals k. So S sub k is equal to 1 squared plus 2 squared plus all the way up to, I'm going to put a k in there and say k squared. I'm going to assume that that would actually be equal to k times k plus 1 times 2k plus 1 over 6. Okay, that's an assumption, and I'm going to use substitution with that later. I must show the ability to get to the next step on the ladder. That's what I must show. I must show that S sub k plus 1 is equal to all of this with a k plus 1 in it. Oh, here we go. K plus 1 where there was a k. K plus 1 where there was a k plus 1. And then 2 times k plus 1 plus 1, and it's all over 6. I got to show that that's true. Okay? S sub k plus 1 is, if I'm going to do this again, but I'm going to go until I hit a k plus 1, I'm going to have 1 squared plus 2 squared plus dot dot dot. I'm going to get up to the k squared, which is in my assumption. There's the first k terms, but I've got to show this is true for one more term, so I got to put a k plus 1 squared in there. I've got to put a k plus 1 in there in that formula and say that that's got to be equal to this that I just wrote. But I'm going to simplify it a little. K plus 1 times k plus 2 times 2k plus 2 plus 1 is 2k plus 3 over 6. I got to show that those two things are equal. Well, again, I made an assumption that the first k terms are worth this. So I go k times k plus 1 times 2k plus 1 over 6 plus k plus 1 squared has got to be equal to this k plus 1 times k plus 2 times 2k plus 3. I thought I was going to start this and then let you go, but that just didn't happen, did it? Okay, so you guys here, we got a choice. Okay, what we need at this point is for these two sides just to be equal. We could multiply everything out, which would take longer, or we could try to make this one look like that one. It's starting to feel a little like a trig identity, isn't it? Sorry to say that. Wouldn't this have 6 in front of it? It would. Okay, so I would have k times k plus 1 times 2k plus 1 over 6 plus 6 times k plus 1 squared over 6, so that I have common denominators, is equal to k plus 1 times k plus 2 times 2k plus 3 over 6. Okay, can I make this look like that? That's where we're at. I got a 2k plus 3. I don't have a 2k plus 3 there. That's a bummer. So, I think I'm going to have to multiply all this out and see if it factors like that. There's a k plus 1 here. There's a k plus 1 here. Okay, watch. I got a trick. All right. I'm going to write over 6. But I'm going to run out of room. We're going to have to go to the next page. Sorry about this, guys. I'm going to take k plus 1 out of both of these two terms. Okay, if it's out from here, look what's left before this plus sign. K and 2k plus 1. Then there's my plus sign. And what's left here is 6 times only 1k plus 1. That's equal to k plus 1 times k plus 2 times 2k plus 3 over 6. Okay, so now what I did by taking a k plus 1 out is I just need the rest of this to equal that part. See, I'm just doing a little trick. You can, if you want, multiply it all out to see if it's all equal. That's fine. Let's see. How can I do this? I don't want to... I need to flip this over, but I want you to see where I was. So I'm going to write it on the back of this last page. This was the page 2. So I'm going to go to page 2. I'm going to say this is the end of... Actually, it's page 4, isn't it? End of page 4. Okay, so here's where we were. We had k plus 1 times... You don't have to write this because I'm just copying it. 2k plus 1 plus 6 times k plus 1. All of that's over 6, and all of this is over 6. And the second these are shown to be equal to each other, the proof is over. 2k plus 3. Okay? And I have k plus 1's isolated. So if I can just multiply this out and show that it factors to that, we're done here. So I'm going to go k plus 1, and I'm going to multiply all this stuff out. I have 2k squared, k times 2k, and then plus k, plus 6k, plus 6. All of that over 6 is equal to k plus 1. This is one of the longer proofs that we're probably going to do. So I picked a real winner to work on today. By the way, we could get rid of the 6's. We could multiply by 6. We just need these sides to be equal. So this would be k plus 1 times 2k squared plus 7k plus 6 over 6 is equal to k plus 1 times k plus 2 times 2k plus 3, and it's all over 6. I want to factor this. Here we go. K plus 1 times. I set up 2 sets of parentheses. I have k plus 1, and I set up, well, I don't have to set anything up. I need it to equal this. So there's kind of a hint. Hey, this is supposed to look like that. So I'm going to put a k here and a 2k here because it's supposed to look like that. And look, isn't k times 2k 2k squared? I need these to multiply to be a 6. Hey, I got an idea. Let's call this a 2 and a 3 and see if it works out. If I make these pluses, I have 2k squared. I have 3k plus 4k, which is 7k, and plus 6. This side is equal to that side. Again, if we wanted to, when we got to this point, we could have just made this 6 over 6 and then just multiplied everything out. We could have done that, and it might have been faster, but we'd have had to write more stuff. Okay? I am going to make an assignment for you. I would like you to just try to do one of these tonight. All right? Just give me an honest effort. So on page 889 in this book, I would like you to try. Look, there's no squared. There's no craziness here. Just go through the motions and see if you can do this with number 2. That's your job today. I definitely want to do this in both classes, A and B day, so that we can do this on Thursday with you guys in the room with me, and we can do it on Friday. And then we'll probably be done with it. And then next week, I know we got the SAT in the middle, but we can do some review stuff and a test for Chapter 12. All right? Have a good day, everybody.